have one more tutorial on UR in 2 weeks time. So in which class we will end. Okay. Let us start. 5 questions for today, right? I will cover question 1, 2, 3 for today. 2 to 5 for next week. And finally, week 12 is UR question. Let us start. With question 3, then we will move on to question 1 and 2. So if you have not realized it, this is a tutorial on interrupt. I hope you have seen the question. So we have seen how to use an interrupt. We have briefly explained about the purpose of interrupt, right? Meaning, in our while loop, we don't check for condition. Instead, the interrupt can happen anytime. When it happens, the handler will occur. So, interrupt will lead to an interrupt handler. Actually, how does this happen? For example, an interrupt occurs from SW3. How does it know that you're dealing with GPIO interrupt, for example? Let's say an interrupt comes from something else, and maybe your USB port. How does it know it is a USB interrupt handler that it needs to look at, and how does it know where the codes for this are located? Or in other words, an exception or interrupt occurs from system. How does it know it needs to go to system handler? Of course, your system handler consists of things like MSX++. So a system interrupt occurs, it needs to know where that function is located. Meaning, where should I look inside memory in order to find this instruction? Your system handler is MSX++. In assembly, it may consist, for example, of add, load, move, and so on. So this MSX++ is converted to some assembly language. And let's say each line of instruction is located at a specific memory location. For example, maybe for MSX++, maybe you need to start here. So this is a starting address. Then address. After doing this, it will move to the next instruction, which is load, then add, then something else. Basically, the assembly instructions will allow you to increase MSX++. So when your interrupt occurs, the system interrupt occurs, you need to know that the first instruction, or rather the starting address of the system handler is located somewhere. How do you know where this address is? How do you jump to this instruction? This is where a vector table is helpful. So when it cystic interrupt occurs, it will look at a vector table. The vector table will tell it where the starting address is located. It will tell it you need to start from this instruction and you proceed on. So that's the purpose of the vector table. Simply tell it where to start. So let's look further. The vector table itself is in your memory. Okay? Memory address, memory data. So this is an address, this is a data. It's what we have always been seeing since the very beginning. It's more like you have a big memory, you have many addresses, many data. A small set of it is reserved and it is called a vector table. So it is this called vector table. Let us say, for example, cystic interrupt occurs. The cystic interrupt occurs. Okay. Well, what is cystic? Cystic is interrupt ID 15. No, cystic is 15. Like we have seen for EE2024E in lab, it is 21, right? Here, cystic is 16. Actually, what will happen is cystic, no, 15. It will do some calculation. 15 times 4. What is 15 times 4 is 60. Okay? What is 60 in binary? So 60 in binary is, let's see, 32, 60, 8, 4, 2, 1. So it should be 1, 1, 1, 1, 0, 0. Right? So 32 plus 8 is 40, plus 16, 56, plus 5 is 60. 60 in binary is this. What do you notice here? So this is in binary. 60 is in decimal, is binary. And if we convert it to hexadecimal, it is 3C. So when our cystic interrupt occurred, we figured out I need to do 15 times 4 bytes because we know each location is 4 bytes. So 15 times 4 is 60. 60 in hexadecimal is 3C. So I will look at the address 3C. Where is 3C? So 3C is here. 3C tells me this is cystic. Actually, the thing that it tells you here is the starting address for the cystic handler. So maybe it tells you the starting address for the cystic handler is, let's say, 0x, maybe 1, 0, 2, A, B, C, D, E. For example, so it tells you this is the starting address of cystic. Therefore, what your program will do it will look at this address in memory. So somewhere in memory, at this address 0x1 0 2 A B C D E. Okay, at this starting address, this is where the first instruction for cystic is located. For example, like we saw here previously. Where was it again? Okay, I will mention it again. For example, maybe the first instruction for cystic is at and maybe move, then maybe load, and maybe some other move, and so on. Okay, basically your MS-DIX++ in assembly, it will look like this. The first instruction maybe is add, then maybe is move, I'm not sure, but it is converted to assembly. So what will happen is the vector table has simply indicated to you the starting address of the system handler. It knows the starting address of the system handler. Therefore, it can start to do the instruction add, move, load, move, and so on. Basically, this is a system handler function. Whatever you have written inside the handler function, it is stored here, so you will do it in sequence. Okay. Similarly, if you have an interrupt from, let's say, some other device, for example, what is the interrupt of EINT3? Well, EINT3 is, let's have a look. So EINT3 is number 21. Sorry, EINT3 is number 37. Okay, number 37. So you will do 37 times 4 in hexadecimal, you will get some value. So it's like in hexadecimal, you will get some value for EINT3. It will tell you the starting address for EINT3 handler. So it will tell you some starting address. Therefore, in memory, you will look for that starting address somewhere in between. Or maybe it can come from something else. So one last time, maybe it comes from IRQ1. So if it comes from IRQ1, well, what is IRQ1? So interrupt the first one is you have to look at the user manual also. So let's look at the NDIC. IRQ1 is the timer 0. Okay. IRQ is not the same as interrupt number. IRQ1 here is referring to the timer. So IRQ1, or in other words, interrupt ID, it refers to the timer. Meaning, suppose you had an interrupt from the timer. This is like a system. For example, it will interrupt you every time, every maybe 1 second, or maybe every 0.5 seconds, and so on. So if you get an interrupt from IRQ number 1, which is a timer, you get an interrupt from IRQ number 1, it will take this exception number 17 times 4, you will get some value. In hexadecimal, it is 0x44. So in hexadecimal, for example here, IRQ, you will get 0x44. So here you will have the starting address for IRQ1, which is starting address for the timer handler function. For example, 0x1110 ABC ABBB. So if we look for that address somewhere here, maybe it is here, 0x1110ABCD. And it has a first instruction, meaning the first thing it needs to do, and it proceeds on terminal. So this is the purpose of the vector table. Is it clear for everyone? Meaning, if you have an interrupt, it tells you the starting address of the handler function for that interrupt. An interrupt occurs, it will do some calculation to find the address in the vector table. The vector table tells you the starting address of that handler function. Therefore, you look for that starting address of that handler function and you proceed on and do the instructions. Alright, is it clear? That's a vector table. And I have mentioned it many times. When you have an interrupt, ID, or rather, when you have an interrupt number, you multiply it by 4, you plus the vector table starting address, you will have the vector table address you need to look at, which is here. Where do you need to look at? The additional thing you have seen in this formula here, instead of just a multiply by 4, there is a VE4R, okay? Vector table offset register. By default, this is 0. So if this is 0, it might be it doesn't exist. So it is simply interrupt number times 4. The vector table offset simply means that here, if your vector table offset is 0, it will start here, okay, 0. If you offset it maybe by 8, if you offset by 8, basically your vector table has been offset by 8. This will, basically everything has been offset by 8 bytes. So even this, everything will be offset by 8. In our case, or rather for our module, we don't really need to worry about it. We assume here it is 0, 0, but if ever they tell you it is offset, you need to know what it is. So by default, if we don't say anything, the offset is 0. So if we don't say anything, this is 0 plus 0. Well, if you have an interrupt number, once again, what I just said was you multiply by 4, you have a decimal value, you convert to hexadecimal, and you get the address you need to look at in the vector table. And the vector table will tell you the starting address of the handler. Okay. Now, take note of this thing. There's something called an interrupt ID, something called an exception number. Interrupt ID can also be called I or Q. Exception number can also be called interrupt number. Interrupt number and interrupt ID are not the same thing. Okay, they are different. The relationship between this one and this one for our 1769 is quite simple. It is simply interrupt ID plus 16. Okay. So what I meant was exception number is the same thing as interrupt number. Interrupt ID is the same thing as I or Q. But interrupt number and interrupt ID are not the same thing. Okay? So this is a bit confusing, but even I'm still confused. So it's just to let you know that there's a difference. You cannot simply say number is the same as ID. Okay, the focus here was on the vector table and offset. Alright? Is it fine? If it's fine, I will move on. Can I move on? Okay. Move on. Alright, let us look at preamp. So I have just question 1 and 2. Then next week I will cover question 4 and 5. What is preamp priority, sub-priority, effective priority? Maybe let us have a look at how it affects our priority level. How setting the preamp priority field or sub-priority field will affect the priority of our interrupt. Let us say, or rather, when we talk about interrupt priority or preamp priority or sub-priority, let us consider 8 bits. Actually, it is 32 bits, but this one will be covered in lecture. Let us say it is 8 bits. When you deal with this thing, you will say it is 8 bits. The question tells us, assume your IPR width, the interrupt priority register width, is 2 bits, what does this mean? If it is 2 bits, we are going to look at the 2 most significant bits. Okay, IPR width is 2. If it is 5 bits, we are going to look at the 5 most significant bits. And of course, if it is 7, it means we are looking at the 7 most significant bits. In our question, we are told it is 2 bits. Okay, 2 bits. What other information do we have? 2 bits, right? So, other information is priority group 6. Group 6 means sub priority must be 6 to 0. So let's see. Group 6 means the sub priority must be 6 to 0. Of course, group 4 means sub priority is 4 to 0. So similarly, 2 means sub priority is 2 to 0. Here, we are told to use priority group 6. So bit 6 to bit 0 is sub priority. Bit 7 is preamp priority. So if we look here, sub priority is bit 6 to bit 0. So bit 6 to bit 0 is sub priority. Bit 7 is preamp priority. So bit 7 is preamp. Okay. Well, everything is now settled. But, like we said, since the IPR width is 2, it means we are only looking at the 2 most significant bits. We ignore all the rest. Whether it's defined as sub-priority or not, it doesn't matter. We are only looking at bit 6 and 7. What are the possibilities for preamp priority bit? So for preamp priority bit, meaning bit 7, 2 possibilities. It can be 0 or it can be 1. Let us look at the sub-priority bits. What are the possibilities? It can be 0, it can be 1, when your preamp is 0. Similarly, it can be 0, it can be 1, when your preamp is 1. So, in all, what is the effective priority? Effective is simply this one plus this one. Plus can also be looked at as 4. Okay, bitwise 4. So this one plus this one, you have your effective priority. Similarly, this one plus this one, you have your effective priority. Then this one plus this one, you have an effective priority. This one plus this one, you have an effective priority. In all, you have these possibilities. For example, 00x, 40x, 80x, C0x. These are the possible interrupt levels you can have. So you can have 4 different interrupt priority. Right here. 4 interrupts, 4 possible levels. And we have summarized it here. For preamp, it can be 0, 0. So 0, 0, 8, 0, 8, 0, 8, 0. For each case, the sub-priority can differ. 0, 0, 40. So 0, 0, 40. Here it is 0, 0, 40. So 0, 0, 40. And of course, effective priority is this one plus this one, you get an effective. Or basically, you're combining these two together. The green color one and the purple pink color one, you're combining them together. So you have 4 possible interrupt priority levels. This one has higher importance. This one will happen first. Then this one is next in line, this one is next, and this one is next. Basically, this has the highest priority. It will occur first. The lower the value, the higher the priority. Alright? Let's look at further example just to make it clearer for you. IPR width is 2 once again. So IPO width is 2 most significant bits. We are going to use priority group 3. Priority group 3 tells us preamp is bit 7 to 4. So preamp is bit 7 to 4. Sub-priority is bit 3 to 0. So bit 3 to 0 is sub-priority. We ignore these bits because they are outside our IPO width, which is just 2 bits. So we ignore it, we are left only with these 2 bits. So this one is a preamp priority bit. This one also is a preamp, but it is ignored because it is outside our preamp. This one is a sub-priority. It is ignored because it is outside the preamp. So what are the possibilities for preamp? 2 bits means 4 possibilities. So these are the possibilities. Sub-priority, there's no bits that can be changed for sub-priority here. So it's only 1 possibility. Effective priority is simply this one plus this one, you get an effective. This one plus this one, you get another effective, and so on. Since this is 0, basically this is equal to this. Once again, 4 levels. This, and this. 4 possible levels. So it is summarized here. 4 possible levels. Proceed on with another example. So now it's obvious. 2 bits, so 2 bits. Priority group 1. So if we set priority group 1, it means sub-priority is 1 to 0. This is sub-priority. 7 to 2 is preamp. So 7 to 2 is preamp. Like we said, we are looking only at these 2 bits because IPO width is 2. What are the possibilities here? Once again, it's the same thing. There's only some bits for preamp, no sub-priority, and you have the effective. Next example, same thing. Again, same thing, 2 bits, so 2 bits. Preamp, none, so there's no preamp. Sub-priority, 7 to 0. So all these are sub-priority bits. Okay, all of them are sub-priority. What are the possibilities for preamp? Only 0. Okay, there's no other possibility. Possibilities for sub-priority? Well, these are the possibilities for sub-priority. And the effective means this one plus this one, and this one plus this one. Then you have this one plus this one. So for each one of these, you have an effective priority. Okay? Is it clear for everyone? Quite obvious, right? Yes.
The table will always be given, right?
The priority
table.
easy to memorize, right?
Memorize it. It's not given.
I think it will be given, but it's easy to memorize. Priority group 7 simply means 7 to 0 is a priority. You just look at the group number, it means anything below that is a priority.
Oh.
But I think it should be given. But it's easy to memorize anyway. But if you need to memorize so many tables, then it is difficult. Yeah, I hope it will be given. I believe it will be given to prevent errors. You are more concerned about testing your understanding rather than your memorization. So you don't need to memorize, but just in case, maybe just reserve a bit of space in your brain for this, just in case. Usually it will be given. Alright. Let us look at it slightly more. Our 1769 makes use of the cortex M3. So this is made by NXP. When it was made by NXP, NXP reserved 5 bits for the priority bits. Maybe some other manufacturer, let's say, if some other manufacturer make use of the cortex M3, maybe they may reserve just 3 bits for the priority. Maybe this is STM, or maybe someone else like Texas Instrument. Maybe for them, they may reserve 7 bits. We don't know. I only know that LPC 1769. But different manufacturers can set different values. We cannot change it. Okay? It's a manufacturer who will set it. Let's say our Cortex M3 made, or rather used by NXP, has reserved 5 bits for the 1769 priority bits. You can find it inside your library files. So I'll show you here. XX is inside CMSIS. So over there, if you look at, okay, these things are all specific to the 17XX. It has nothing to do with the baseboard or the MCU. Okay? Baseboard is a big blue board, meaning the external device, light sensor, accelerometer. MCU is a peripheral which is connected to your processor, which is this processor, 1769 Cortex M3. So MCU, or rather peripherals, include I2C, GPIO, USB, ADC, and so on. Then you have the CMSIS, which is basically the processor without any connections, no GPIO, nothing else. It is just a processor. And they have defined for the processor some interrupt. For example, EE2024E is number 21. Later on, you will see there's only one processing unit, or even the NDIC is 5 bits. These have been set by the manufacturer. You must never change this thing. But if you change any value, everything does not work. So this is set by the manufacturer, nothing can be changed. So in this question, we are told that our LPC 1769 uses an IPR width of 5. This is the IPR width. So it is 5 bits, 5 most significant bits. This cannot be changed. It must be 5 bits for the 1769. Of course, if it is another manufacturer, like we said, maybe Texas Instrument uses 7 bits. Maybe STM uses 3 bits, all depends. So here we know that IPR. Then we are told to look at priority group 5. Somehow, 5 and 5, they have nothing to do with each other. They are independent. But in our question, we ask you to use priority group 5. Okay? This 5 and this 5 have nothing to do. Okay? So priority, this is the IPR width here. Then we're told to choose this grouping. So this grouping tells us bit 5 to bit 0 is sub-priority. So bit 5 to bit 0 is sub-priority. Okay, let me use another color. 5 to 0 is sub-priority. 5 to 0 is sub-priority. And 7 to 6 is preempt priority. Preempt priority. So if we look at it, the priority preempt, our IPR width is 5. So we consider only these 5 bits. Possibilities would be here. Preempt, 2 bits means 2 to the power of 2 possibilities, so 4 in all. 2 bits are used, so there are 4 possibilities for the preempt. 0, 0, 0, 1, 1, 0, 1, 1. 4 possibilities. which is over here. So priority, we have 3 bits. 3 bits means 2 to the power of 3 possibilities. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. We have all these possibilities, 8 in all. And as always, to get the effective priority of each case, with plus, for example, with the first case, we get 1 effective level. With plus with the second case, we get another effective level. Here, we get another 1. So you have 8 possible cases, then you select the second one. So for the second one, you have another 8 possible cases. You select another one again, for the third one, another 8 possibilities. So you will have 4 possibilities and 8 possibilities. In all, you have 32 possible values or 32 possible priority levels. So these are the 32 levels you can have for the priority field. Okay, 32 priority level. Any questions here? Because if you have understood the first question, then this is straightforward. So we have shown you how to write down all these values. First, you need to know the IPR width. IPR. So we know the IPR width, 5 bits, for example. Then we need to know the grouping. If we are looking at grouping 3, then it means bit 3 to bit 0 is sub-priority. Bit 7 to bit 4 is preamp. If we are looking at group 5, well, this bit is sub-priority, this bit is preamp. We can determine which bit is sub-priority and which bit is preamp. Those outside the IPR width, we ignore them. And for preamp, we check all the possibilities. For sub-priority, we check all the possibilities. This one has 4 possibilities, this one has 8 possibilities, okay? 2 to the power of 2, 2 to the power of 3. Or you look at it this way, 1, 2, 3, 4, 5. So the effective priority is 2 to the power of 5, so 32 possibilities. Okay, is it fine before we proceed on? Let me explain a bit about the sub-priority and preamp now. It was covered in the lecture, but let's try to look at it once again. I will take a basic example. So let me assume that IPR width is 4. I will assume it is 4, therefore I will look at the 4 most significant. Right. Let's assume I'm choosing the priority group number 5. So if I choose priority group number 5, bit 5 to 0 is sub-priority, bit 7 to 6 is preamp. What are the possibilities here? Sub-priority, these are the possibilities. Preamp, these are the possibilities. Sub-priority, these are the possibilities. So, 0, 0 has the highest priority, C0 has the lowest priority. Similarly here, for sub-priority, 0, 0 has the highest importance, 1, 1 has the lowest importance or lowest priority. Now, okay, these are the possibilities, right? 0, 0, 4, 0, 8, 0, C0. 0, 0, 1, 0, 2, 0, 3, 0 when you convert it to hexadecimal. Let us take a scenario. Let us say currently my processor is dealing with an interrupt. For example, maybe I'm dealing with an interrupt from maybe a USB device or maybe a switch. Let us say it is dealing with this interrupt, which happens to have a preamp of 40, sub-priority of 10. Meaning it has a preamp of 40, a sub-priority of 10. So this is a current interrupt being handled by the CPU. 40, 10. 40 for preamp, 10 for sub. If ever we need to interrupt this interrupt, or basically put it on hold because there's a higher priority interrupt, I will display it in this manner, okay, just for understanding purpose. Meaning, if this needs to be suspended for some time or interrupted for some time, I will separate it, meaning this is separated into two. So this is how I will illustrate things in the example. So let us see what happens now. Remember, currently our CPU is processing this interrupt. Let's say a new interrupt comes in. The new interrupt, you have set maybe the preamp priority, or we call it group priority. It is the same thing. Group priority and preamp priority is the same. So let's say the group priority or preamp priority is 80. The sub priority is 0, 0. What happens here? This one is currently being handled by the processor. It will check the priority. The new interrupt has a higher value. Because the value is higher, the priority is lower, or importance is lower. Since the importance is lower, it will just carry on with its current interrupt and only process this new interrupt afterwards. Okay, because this has a lower importance. 80 has a lower importance than 40. In this case, it doesn't even bother about the sub-priority. It only looks at the group priority first. It always looks at the group priority first. Another example. This comes in. Group priority is 0, 0. Sub-priority is 0, 0. It checks the group priority. Currently, my handler or my source being handled is 40 hex. Somehow, this interrupt comes in, which has a value of 0, 0, which means a higher priority. So this one must be processed first. So the current task is suspended, it's on hold. We perform the new interrupt. After it is done, we go back to the old task and continue. Okay, so this is what happens when the interrupt with a higher preamp priority comes in. How about one with equal priority? So currently I'm doing 40, 10, but a new one with 40, 0 comes in. What will happen here? Well, it compares 40 and 40. Since the new interrupt has the same group priority as the current interrupt, it will be placed on hold. This will wait, no matter the sub-priority. Even if the sub-priority is lower, has a lower value than this one, it doesn't care. It will check only the group priority first. It is equal. Since you're both equal, therefore, you have to wait. I will finish my current task, and then I will deal with the new interrupt. So conclusion is, if the value is higher or equal to the current value, therefore you must wait. But if the value is lower than the current value, then I will suspend my current task and I will deal with a new task. Okay, up to now, it is time for everyone. We have seen this cases. An interrupt with a higher value comes in, you have to wait. An interrupt with a lower value comes in, well, you have more importance, therefore, I suspend the current task, I will deal with a new vectors first. An interrupt with equal group priority comes in. Well, since you're equal, you have to wait. I don't care about the sub-priority. How about pending interrupts? Here I'm telling the interrupt to wait, right? What if while this one is going on, many more interrupts comes in? So this one is still being carried out, then you have 3 or 4 more interrupts to wait. So your interrupts has to wait, right? Some of them have to wait. Let us have a look. Suppose these are the new interrupts which is coming in. A new interrupt with 4020, a new interrupt with 4000, another interrupt with C0, and so on. If you check all these interrupts, somehow you see that the group priority or preamp priority is greater than or equal to the current interrupt priority. Because it is greater than or equal to, it has to wait. So all these, this is waiting, this is waiting, this is waiting, this is waiting, and this one also is waiting. Because all of them have greater than or equal to this value, so they have to wait. Now, why is your waiting? So all these are waiting. If you look at it, you can notice something. C0, C0. So the preamp are same. Actually, which one do you think should occur first? For example, if we look over here, which one should occur first? Should it be first come, first serve? Or is there something else we need to check? So it is not first come, first serve. That's where the sub-priority comes in. It's only for pending interrupt. For pending interrupt, meaning if your interrupt are all waiting here, the sub-priority will determine the order. So if it is 4040, first of all we check all the group priority or preamp priority. 4040, after that, what comes after that, it is 80. After 80, it is C0, C0. Now, the 4040 both are same. Which one comes first? We look at the sub-priority. This one should happen first, it has a lower value. Then comes this one. Next, we look at 0x80. There's only one possibility. Next, we look at 0xC0. So two possibilities. Which one comes first? This one has a lower value. So this comes first, followed by this one. So ultimately, this is what you get. This one, after it has completed itself, it will do this one, 4000, then it do this one, 40020. As you see here, this is lower than this one. Next, it performs this one, 0x80, because 80 is more than 40, so it has a lower importance. Then next, it performs this one, 0xC0, because it has a lower importance than this one. So it performs 0xC0, then the sub-priority is 20 and 30. Because while they were pending, their order had been rearranged first by looking at the group priority, or first by looking at the preamp, then by looking at the sub-priority. Sub-priority is important only for pending interrupts. Is it okay up to now? What happens if we have let's say (4020), same group, same sub. What else? 40 40, 0. Same group priority, same sub-priority. Well, in this case, once again, what do you think? Do you think, let's say, which one do you think will happen first? Let me check the example. 40, 20. This one is 40. Okay. So, when we look at all these, we know this one should occur later because the group priority is higher, right? So, this one will occur last. Then the rest are all 40, 40, 40. Because they're all 40, 40, 40, we look at the sub-priority. So which one happens first? We have 0, 0, 0, 0. So one of these two will happen first. After these two have been completed, it is 20 and 20 which will be carried out. But among these two, which one will happen first? Similarly, among these two, which one will happen first? How will it be rearranged? Is it small? Not sorry, yes. So between this one and this one, next. So let's see. Which one will be carried out first? Between this and this, we don't know. Between this one and this one, which one? Once again, there's no such thing as first come, first serve here. Each one of your interrupt has a unique ID, which is called the interrupt request number. IRQ10, IRQ11, 5, and so on. All of them have a unique ID, as you see over here. So, for example, if it's coming from your EE2024E, it has 21. Okay. So it has 21. How about external interrupt 0? It has 18. Something else, maybe the motor control, the PWM, has 30. If you look up, maybe the timer 0 has 1. Watchdog timer is 0, for example. Well, in our lab, we have never configured the sub-priority or group priority. So for our lab, for our assignment, it means everything sub-priority or group priority was 0. However, there is still a priority level. Just like preamp and sub, they are equal. Just like over here, preamp and sub, they are equal. So in this case, what you need to look at is the IRQ number. The lower the IRQ number, the higher the priority. So over here, this one and this one are same, but the IRQ number are different. This is 11, this is 8. So the one which will occur first is IRQ 8 because it has a lower value than 11. So at the end of the day, the order in which you compare things is, first, you compare the group priority. So group priority is the same. Okay, we're talking about pending interrupts. Okay, because sub-priority and IRQ is not applicable for interrupts which are not pending. It's only for pending interrupts whereby you check the sub-priority and IRQ. So first you check the group priority. If they are equal, you check their sub-priority. If they are equal, you check their IRQ number. And IRQ is unique. Each one of it is unique. Because of course, a timer has more importance than maybe a switch. because the timer is much more important. So, even if you don't configure your sub-priority or group priority, the IOQ number can still determine the interrupt priority for pending interrupts. Okay. So today we have seen the vector table, meaning if you have an interrupt, you will do some calculation which will tell you where inside the vector table you need to look at. For example, if cystic occurs, I will look at this address to get the starting address of the cystic handler. I know the starting address of the cystic handler. I can perform the instructions. The MSE++ in assembly is a full set of instructions. So it will perform the instruction. So that's the purpose of the vector table. Simply it tells you the starting address of the handler. Then we have looked at preamp and sub-priority, how to get the different levels and so on. And we have also seen what happens if your pending interrupts have the same group priority, have the same sub-priority, what happens in this case when you look at the IOQ number. So this is what we have looked at for today. For next week, I will cover the timing diagrams as well as the introduction to the UART part. Okay? And we will end in 2 weeks' time. So these notes I will send you after next week's tutorial. Last week's tutorial I had not yet sent. I was very busy with all these things, but I will try to do it tomorrow. So, any questions up to now? So, if you have issues, if you have not started on your assignment, you better go to the cleaning sessions quickly. So, you try to start on your, rather, you must work on your assignment as soon as possible. Come to the cleaning session if you have issues. Because frankly speaking, during weekdays, it's a bit difficult to set up some meetings for now. So, at least for now, try to come for the cleaning session if you have issues. And this Saturday, I will be at the cleaning session. If you have any issues with your programming, come over there and of course bring your laptop, bring your keyboard and everything and we will solve it. But you need to have started or something like this. So I will